In 2015, a team at Microsoft Research attempted something ambitious. They took a standard convolutional neural network and scaled it to 56 layers. Logic dictated that this deeper network should be more powerful than a 20-layer version. But the results were disturbing. The 56-layer network wasn't just worse on the test set, which would imply overfitting. It had higher training error. The deeper model couldn't even memorize the data as well as the shallow one. This observation threatened the core premise of deep learning. To understand why this was so strange, look at the trend up to 2015. AlexNet won ImageNet in 2012 with just 8 layers. By 2014, VGG pushed to 19. The theory was sound. Deep networks represent a hierarchy of features. Layer 1 sees edges. Layer 5 sees textures. Layer 30 sees objects. Mathematically, a deeper network represents a strictly larger family of functions. It should always be capable of performing at least as well as a shallow one.
Let's be precise about the failure mode. If the 56-layer network had low training error but high test error, that would be overfitting, the model memorizing noise. But that is not what happened. The 56-layer network had high training error. This is called the degradation problem. It means the optimization algorithm, stochastic gradient descent, is failing. The model has the theoretical capacity to learn, but the optimizer is hitting a ceiling it cannot break through.
Here is the thought experiment that proves this is an optimization failure. Imagine a trained 20-layer network that performs well. You can build a 56-layer network by copying those 20 layers exactly and setting the remaining 36 layers to be identity mappings, layers that just pass the input through unchanged. This constructed network behaves exactly like the 20-layer one. The solution space contains the optimal answer, but the solver can't find it. It turns out, forcing a stack of non-linear layers to learn a simple identity function is surprisingly difficult. Kaiming he and his team realized, if learning an identity mapping is hard, don't ask the layers to learn it. Instead of trying to learn the final mapping h of x directly, let the layers learn the residual, or the difference, f of x. We do this by adding a skip connection, a literal wire that takes the input x and adds it to the output. The final output becomes f of x plus x. If the optimal function is the identity, the layers just need to drive their weights to 0. And driving weights to 0 is easy. Weight decay does it automatically. This creates the residual block. In ResNet 18 and 34, it looks like this: a 3x3 convolution, batch normalization, ReLU, another 3x3 convolution, and batch normalization. Then we add the input x. Finally, a ReLU activation is applied after the addition. But there's a catch. What if the input has 64 channels, but the output has 128? You can't add matrices of different sizes. To fix this, we use a projection shortcut, a 1x1 convolution on the skip connection that resizes x to match the output. In the paper, this is known as option B.
For truly deep networks like ResNet 50 and 152, computation becomes the bottleneck. Stacking hundreds of 3x3 convolutions is too expensive. The solution is the bottleneck block. Instead of 2 3x3 layers, we use 3. First, a 1x1 convolution squeezes the channels, say from 256 down to 64. Then, the expensive 3x3 convolution runs on just these 64 channels. Finally, another 1x1 convolution expands them back to 256. The skip connection jumps over all 3. This design reduces the computational cost of the 3x3 layer by roughly a factor of 3, allowing us to go much deeper.
Why does this simple addition work so well? The answer lies in calculus. When we train using backpropagation, we calculate gradients via the chain rule. In a plane network, gradients are multiplied by weights at every layer. If weights are small, the signal vanishes exponentially. But with a skip connection, the gradient equation changes. It becomes the gradient of the layers plus 1. That plus 1 represents the skip connection. It acts as a gradient highway.
ensuring the error signal flows backward to the earliest layers without decaying, no matter how deep the network is.
Later research gave us two more perspectives. First, a ResNet behaves like an enormous ensemble of shallow networks. Because paths can skip layers, 110-layer ResNets effectively contains 2 to the power of 110 different paths. Removing one layer doesn't break the network because valid paths remain. Second, in 2018, researchers visualized the lost landscape. Plain deep networks have chaotic, rugged landscapes full of traps. ResNets smooth this surface out, making it convex and easy for the optimizer to slide down to the global minimum.
The results were undeniable. In the ILSVRC 2015 competition, ResNet crushed the opposition. An ensemble of ResNets achieved 3.57% top 5 error on ImageNet. For context, human error is estimated at around 5.1%. It was the first time a machine beat human-level performance on this task. This architecture became the backbone for detection, segmentation, and future variants like ResNext. Today, if you download a pre-trained model for computer vision, there is a very high chance it's a ResNet.